In Chapter 2, Molecular Collisions, so this chapter will cover the concept of hard-sphere collisions, mean free path, collision frequency factor, collision diameter, Graham's law of efficiency, Fick's law, flux, Fraser of ideal gas, and Knudsen method. As we know, kinetic energy is an expression of the fact that a moving object can do works on anything it hits. It quantifies the amount of works that the object could do as a result of its motions. The total mechanical energy of an object is the sum of its kinetic energy and a potential energy, so that the total kinetic energy is the sum of the translational kinetic energy and rotational kinetic energy of an object. The kinetic molecular theory of gas assumes that the ideal gas molecule is composed of a large number of identical molecules moving in random directions in speed which does not change, spread by distance that are large compared with their size. The volume occupied by the molecules of gas is negligible compared to the volume of the gas itself. This theory also assumes that the molecule undergo perfectly elastic collision, which is no energy loss, with each other and with the walls of the container, but otherwise do not interact. So when two molecules collide, the change of their directions and kinetic energy, but the total kinetic energy is conserved, which is collisions are not sticky. Molecules obey a Newton's law of motions. This means that the molecule move in straight lines until they collide with each other or with the walls of the container. Kinetic energy is the energy an object has because of its motions. If we want to accelerate an object, then we must apply a force. Applying a force requires us to do works. After work has been done, energy has been transferred to the objects, and the object will be moving with a new constant speed. The energy transfer is known as kinetic energy, and it depends on the mass and speed achieved. The kinetic energy can be transferred between objects and transformed into the other kind of energy. The total kinetic energy of a mass can be expressed as the sum of the translational kinetic energy of its center of mass plus the kinetic energy of rotationals about its center of mass. The ideal gas law assumes that the particles are not interacting, which is the only interactions between the ideal gas molecules will be an elastic collisions, opens impact with each other, or an elastic collisions with the walls of the containers. This means that they can all occupy the same space, but this is not realistic because the gas particles themselves occupy some volumes. And in most circumstances, this volume is a tiny fraction of the total volumes, and thus it can be ignored. In contrast, if the total volume is shrinks, then the volume of the particle will become larger. Deviations of real gas from ideal behaviors. The behavior of real gas usually agrees with the predictions of the ideal gas equations to 85% at normal temperature and pressure. However, at low temperature and high pressure, the real gas deviates significantly from ideal gas behavior. In 1873, while searching for a way to link the behavior of liquid and gas, the Dutch physicist Johannes van der Waals developed an explanation for these deviations and an equation that was able to fit the behavior of real gas over a much wider range of pressure. Van der Waals realized that two of the assumptions of the kinetic molecular theory were questionable, which is the kinetic theory assumes that the gas particle occupy a negligible fraction of the total volume of the gas. It is also assumes that the force of attraction between the gas molecule is equal to 0. The first assumptions work at pressure close to 1 atm, but something happened to the validity of these assumptions as the gas is compressed, which is at normal pressure, the volume occupied by this particle is a negligible small fraction of the total volume of the gas. In other words, the molecules of gas are far apart and the intermolecular force are negligible, so that the real gas can behave as ideal gas. However, at high pressure, this is no longer true. As a result, the real gas are not as compressible at high pressure as an ideal gas. The volume of a real gas is therefore larger than expected from the ideal gas equation at high pressure. which is the molecules are pushed close together, that a repulsion force operates between them, making the gas less compressible. Therefore, the real gas cannot behave as ideal gas. In ideal gas behavior, there is no interactions between the gas molecules. The kinetic energy of the molecules and atoms is completely conserved in the collisions between the molecules and atoms. As we know that temperature is directly related to average kinetic energy, which is at high temperature, the molecule have sufficient kinetic energy to overcome intermolecular attractive force, and the effect of non-zero molecular volumes predominates. Conversely, as the temperature is lower, the kinetic energy of the gas molecule decreases. Eventually, a point is reached where the molecule can no longer overcome this intermolecular attractive force, and the gas liquefies or condenses to a liquid. So in short, the negligible intermolecular force is the secrets behind the deviations of the real gas from the ideal gas. As we know, molecules in the gas can interact with each other. Though the interaction is weak at high temperature, yet with the decreasing the temperature, the interaction force will increase. At high pressure also, which is more than 5 atms, these molecules come close to each other, hence leading to a decrease in the volumes. And these interactions between the molecules can prevent them from bombarding on the containers. The attractive force between the molecules can prevent the molecule from colliding with the walls of the containers. That is where the difference between the ideal gas and the real gas become transparent, which is the ideal gas are those gas which follow the gas law, and the molecules of the gas have no interaction with each other, while the real gas are those gas which occupy a space and the molecule have a force of interactions between each other. Note that a small nonpolar molecule such as hydrogen and helium shows the least deviations, while the big polar molecules such as ammonia and sulfur dioxide show a marked deviations from the ideal behavior. According to the Boyle's law, PV constant at a constant temperature. Hence, at a constant temperature, plot PV versus P has to be a straight line, which is parallel to x-axis. However, the real gas do not show such a behavior. From the plot, we can observe that for the gas like hydrogen and helium, PV increase continuously with increase of pressures, whereas gas like carbon monoxide and methane, which is the PV is first decrease with increase of pressure and reach a minimum value and then increase continuously with increase of pressure. Similarly, if we plot experimental value of pressure versus volume at a constant temperature, that is for the real gas, and theoretical calculate values from the Boyle's law, that is for the ideal gas, which is the two curves do not coincide. Hence, two cases arise, which is when Z is smaller than 1, for example for methane and carbon monoxide, the gas is said to show a negative deviations. Therefore, gas shows more compression than expected from the ideal behavior. This is caused by the predominance of attractive force among the molecules of this gas. When the Z value is more than 1, the gas is said to show a positive deviations. This implies that the gas will show less compressions than expected from the ideal behavior. This is caused by the predominance of the strong repulsive force among these molecules. The greater the departs in the value of Z from unity, the greater are the deviations from the ideal behavior. For the same gas at a particular pressure, the extent of deviations depends upon the temperatures. For example, for the nitrogen gas, which is at a temperature increase, the minimum in the curve shifts upwards. Ultimately, a temperature is reached at which the value of Z remains close to 1 over an appreciable range of the pressure. Van der Waals equations was derived by Johannes van der Waals in 1873. The equation is basically modified versions of the ideal gas law, which state that the gas consists of point mass that undergo perfectly elastic collisions. However, this law fails to explain the behavior of real gas. Therefore, Van der Waals equations was revised and it helps to define the physical state of the real gas. More significantly, the Van der Waals equations take into considerations the molecular size and molecular interaction force, either attractive or repulsive force. Van der Waals equation is an equation relating the relationship between the pressure, volumes, temperature and the amount of the real gas. For a real gas containing n moles, the equation is written as P ideals is equal to P real plus A n power 2 over V power 2, which is A is constant, n is the number of moles and V is the volume of the container. The constant A in van der Waals equations provide the corrections for the intermolecular force. Van der Waals constant A is a value measured of the magnitude of the attractive force among the molecules of the gas. There will be a large intermolecular force of attraction if the value of A is large. At low pressure, the correction for intermolecular attraction A is more important than the one for the molecular volume B. At high pressure and small volumes, the correction for the volume of the molecules becomes important because the molecules themselves are incompressible and constitute an appreciable fraction of the total volumes. At some intermediate pressure, the corrections have opposing influence, and the gas appear to follow the relation given by the ideal gas equations, which is PV is equal to nRT over a small range of pressure. The frequency of such encounter increases with the square of the number of molecules per unit volumes because the probability of finding each of two molecules in a particular region is proportional to n over V. Van der Waals constant B is a measure of the effective size of the gas molecules. Constant B adjusts for the volume occupied by the gas particles. It is a correction for finite molecular size and its value is the volume of 1 mole of the atoms or molecules. The corrections to the volume is NB. Note that when V is relatively large, N is relatively small. Both of these correction terms become negligible and the van der Waals equations reduce to the ideal gas law PV is equal to nRT. Such a condition responds to a gas with relatively low number of molecules is occupying a relatively large volumes, that is a gas is relatively low pressure. So NB represents the volume occupied by n moles of the gas. Table shows the van der Waals constant of some common gas. The van der Waals force increased due to the increase in the number of electrons present and the size of the molecules, which means that the larger molecule have a larger surface area of its electron cloud. This is also becoming subject to the stronger van der Waals force. From the table, we can see that helium atoms have the weakest attractions for one another because helium has the smaller A value. This is also a rough relationship between the molecular size and B. Generally, the larger the molecules or the atoms, the greater the B value. But the relationship between B and molecular or atomic size is not a simple one.